Alright, in this video, we're gonna start introducing you the periodic table. Okay, so this is a periodic table. You can see it's not perfect shaped. There's some taller groups, there's some taller columns here. There's some shorter columns. They're usually another separated columns groups. Okay, so first of all, we don't really call them columns. Okay, so each column here we call them groups. Okay, the groups are vertical columns. Okay, now the rows instead we call them periods. The periods are the rows of periods. Okay, so you can see counting from top to bottom, because usually you start from left up corner, starting counting the elements, right? So this is number 1, this is number 2, number 3, number 4, and goes on like that. So how many rows? 7. Okay, 7 rows, or in other words, 7 periods. Okay. Now, usually when we count the groups or columns, okay, we try to separate these taller ones from the shorter ones. Okay, first of all, there's a big block, shorter groups. In the middle, we call them D block elements, or we call them transition elements. Okay, and down here, we call them F block elements. They are also belonging to transition elements. Now, these taller ones, okay, you can see we're trying to number them, number the group number using Roman numerals from left to right. 1, 2, 3, 4, 5, 6, 7, 8. They're usually called the representative elements, or so-called main group elements. Okay, so these are the ones we probably will spend a little bit more time on at intro chemistry, or even possibly general chemistry. Okay, so again, let's focus on the group numbers with main groups only. Okay, 1 from left to right, 1 through 8, and the period number 1 from top to bottom, 1 through 7. Now, other than these numbers, okay, there are some specific groups we try to give them specific names. Okay, for example, the first group, okay, which are hydrogen, lithium, sodium, all of these guys are called alkaline metals. Okay, the second group elements, okay, are called alkaline earth metals, and the very last group, they're called noble gases. Now, second group, they're called halogens. Okay, and usually in any periodic table, you will also find a zigzag line like this, like the red line showing on the screen. Okay, now what this line does is separate, it's the borderline between metals, okay, and non-metals. So all of these elements, including transition metals, including the alkaline metal, alkaline earth metals, even including these blue ones, okay, they're all metals. Now these white ones and orange noble gases, they are non-metals. So it seems like they're way more kind of metallic elements than non-metallic elements, right? That is true. Okay, well, if you talk about number of elements, yes. Okay, so this is basically a general view about the periodic table. Now, what's very useful to us at this point is, I want you to pay attention to this. Okay, so I'm putting another periodic table here to show you what we can utilize the periodic table for. A lot of things. Okay, first of all, if you look at each block, each element, you can get a number of informations, symbols, sometimes names, even possibly, the number of protons, electrons, neutrons, atomic mass numbers are everything like that. Okay, but more importantly, when you look at the periodic table, okay, let's renumber these numbers. Okay, so you're looking at the 1, 2. If we focus on the so-called representative elements, or so-called main group elements, okay, 3, 4, 5, 6, 7, 8. Okay, now let me tell you what these numbers are for. Okay, they actually have a very important but very significant physical meaning. The group number, okay, which represents the vertical columns here. The group number indicates the number of valence electrons of all of the elements in the same group. So what does that mean is, in group 1, all of these hydrogen, lithium, sodium, all these elements, they all have one valence electron. And the same is true with all of the barium, magnesium, calcium, strontium. All these elements, they all have 2 valence electrons. Let's skip the transition metal, okay? Let's completely skip this part. We're also skipping this part as well, okay? Jump to group 3 of the main group. All of these boron, aluminum, gallium, okay, indium, they all have 3 valence electrons. So you can keep counting, okay? These carbon, silicon, germanium, they all have 4 valence electrons. Nitrogen, phosphorus, arsenic, all of these elements, they all have 5 valence electrons. Oxygen, sulfur, selenium, they all have 6. All of these have 7. And of course, all of the noble gases, they all have perfect 8 valence electrons, which is also why all of these groups, the elements in the last group, they're perfectly stable. They're chemically stable because they already have what they want. Okay, so we already said that because of the number of electrons, okay, these guys are going to decide what to do in the chemistry. So for instance, all of the group 1 elements, okay, all of group 1 elements, they tend to form positive 1 charge by losing 1 electron. Okay, all of the group 2 elements, they tend to form cation as well, become positive 2 charge by losing 2 electrons. Since everybody is looking for 8, right? So basically 4 is where it separates, okay, the borderline. When you have 3 valence electrons, like boron, aluminum, they're going to tend to form positive 3 charge by losing 3 electrons instead of getting 5 more. Okay, the only reason is they don't want to get more is because it's harder. Now, when you have 8 valence electrons, they're not going to do anything. So they're going to be neutral charge, 0 charge. When you have 7 valence electrons, like fluorine, chlorine, these guys, they're going to tend to get 1 more electron. Getting 1 more electron is actually making them negative 1 charge. Okay, when you have 6 valence electrons, they tend to get 2 more electrons, become negative 2 charge. Okay, when you have 5 valence electrons, instead of losing 5, they tend to get 3 more. Get 3 more electrons, become negative 3 charge. So you can see the trend here, okay? So they all have possible charges, no matter you know them what their elements is, what this is or not, okay? Now what about these guys? Carbon, silicon, germanium, they have 4 valence electrons. What do they do? Well, of course, they tend to form covalent bond. Because for these guys, either losing 4 electrons or gaining 4 more electrons will be really, really hard, okay? Now, by introducing you this, okay, now we can easily tell if any elements like Ba, you can say, okay, Ba, what is, if it's neutral atom, then it's neutral atom, okay? But if it's ever going to react with anybody, any other elements, what do you think it's going to do? Well, since Ba belongs to group 2, so it has 2 valence electrons. So if you're ever going to do anything with those electrons, it will tend to lose those electrons, become positive 2 charge. Okay, so this is what's really useful to us. When you look at a periodic table, you can actually easily predict what these elements are going to do in the chemistry by defining them to be either positive charge or negative charge, okay, or by losing electrons or gaining electrons. All right, so one more thing here is the period number. Okay, we already said that from top to bottom we number these period numbers. Okay, 1 through 7. Now the physical meaning of the period number is actually how many levels electrons does this element or do all the elements in the same row have. In other words, when you're talking about valence electrons, since valence electrons are on the most outer layer, which layer are they located on? So let's take a look at the example here, okay? Using the first group as an example, we can easily say, okay, all of these elements has 1 valence electron. But we can further introduce you by looking at the period number. So hydrogen has 1 valence electron, which has only 1 electron anyway. So that electron is located on the first layer, of course, right? So hydrogen has 1 electron, but also 1 valence electron, which is located on the first layer, if you look at the period number here. Now, lithium has 3 electrons. I want you to quickly picture the atomic diagram of lithium, okay? It's going to be 2, 1. So you total have 3 electrons. You see this 1 valence electron is located on the second layer, period 2. Sodium has 11 electrons, so the atomic diagram is going to be 2, 8, 1. It also has a 1 valence electron, but this valence electron is located on the third layer, which corresponds to the period number 3. Potassium is number 19, so if you quickly picture the atomic diagram of 19, it's going to be 2, 8, 8. That's 18. 1 more electron. So potassium also has a 1 valence electron, but this valence electron is on the fourth layer, which also indicates potassium has 4 electron layers. Okay. Rubinium, which is number 37, we didn't really learn how to draw atomic diagram any number higher than 20, but still we're able to predict that rubinium has 1 valence electron, which is on the 5th layer. Okay, we may not know all the detail about the layer 1, 2, 3, 4, but we are certain that rubinium has only total 5 layers electrons, and on the 5th layer, which is the most outer layer of it, there's only 1 valence electron. Okay, this applies to all of the elements, not just any group 1. So you can easily say, for example, let's take this one, Sb. Okay, you may not even know what it is, okay, but you can pause here, see if you can figure out how many valence electrons it has and on which layer those valence electrons are located at, okay. So that's right, it's on group 5, so Sb has 5 valence electrons, and those valence electrons are on, its period number here is 5 on 5th level. Okay, 5 electrons on 5th level. And not only that, you can see since it has 5 valence electrons, Sp, if you ever going to be involved in chemistry, you probably tend to, how it's going to become 8? Well, it's going to get 3 more electrons. Probably tend to do this, okay. Possibly, okay. So this is the introduction to the periodic table.